Hello, my name is Shiwan Seok and I will present about the solution of PSIP problems. The table of contents is as follows. Now I will briefly go over the problem description. Let's look at the problem description in detail. We have a digital receiver operating at a sampling frequency of 400 Hz, recording a signal for exactly 1 second. According to the Nyquist-Shannon sampling theorem, this 400 Hz sampling rate allows us to physically observe frequencies up to 200 Hz. Also, a 1-second record means our entire dataset consists of exactly 400 discrete samples. Inside this recorded signal, there is a 20 Hz target waveform that we want to observe. However, it is severely corrupted by a strong 150 Hz interference tone. You can think of this scenario like trying to measure a slow, rhythmic biological signal, such as heartbeat, while a high-frequency machine nearby injects heavy electromagnetic noise into the sensor. In the time domain, this high-frequency noise completely masks the low-frequency target, making direct observation impossible. Therefore, our overall objective to recover this signal is divided into three logical steps. First, we must mathematically prove the existence of these frequencies. We will identify the hidden component by transforming the signal into the frequency domain. Second, we must selectively eliminate the 150 Hz interference instead of using black box function. We will design a precise jet domain filter from scratch by placing zeros directly on the unit circle. Third, even after cleaning the signal, our 400 Hz sampling rate leaves us with low resolution Third, even after cleaning the signal, our 400 Hz sampling rate leaves us with low-resolution discrete dots. We will reconstruct these discrete samples into perfectly continuous analog-like waveform using ideal sensitive interpolation. Let's start with task 1, which is spectral analysis based on the frequency sampling and DFT concepts from lecture 3 and 4. To solve this task, I designed the following code. Since our sampling frequency is 400 Hz, the Nyquist limit is 200 Hz. Therefore, after using the FFT function, I defined the frequency axis up to n/2 to observe the physically meaningful spectrum. As a result, I can show the following figure. In the time domain on the top, the signal looks completely chaotic due to the high frequency noise. However, in the magnitude spectrum on the bottom, the 20 Hz target and the 150 interference signal are perfectly separated and clearly identified as two sharp peaks. Moving to task 2, which is jet domain filter design covered in lecture 5. To solve this task and eliminate the 150 interference, I designed the following code without relying on built-in filter design function. First, I calculated the normalized frequency, V0, which is 150 divided by 400, resulting in 0.375. Then, using Euler formula, I place complex conjugate zeros precisely on the unit circle at this exact angle for eliminating 150 Hz. The Pauli function generates the FIR numerator coefficient b, and the denominator a is just 1. As a result, I can show the following figure. The pole zero map confirms our zeros are correctly placed on the unit circle, which can block interference signal. And if you look at the filtered time domain signal, the 150 Hz noise is completely blocked, successfully extracting the clean 20 Hz target sine wave. Next is task 3, sine C interpolation via zero padding, applying equations 3.27 from lecture 4. To solve this task, I designed the following code. First, I extracted a 0.1 seconds segment, but notice that I started extracting at 0.5 seconds. This is a deliberate choice to bypass any initial transient response caused by the filter in task 2. This leaves us with exactly 40 samples, which is an even number. Mathematically, simply padding zeros in the middle of an even length FFT will break the conjugate symmetry. So in my code, I explicitly extracted the Nyquist bin, divided it by 2, and placed these halves symmetrically. Finally, I multiplied the IFFT result by the expansion factor k plus 1 to preserve the signal's energy, and defined a new 16 times denser time axis, T nu. Finally, task 4 is the visualization of our interpolation. As a result of the mathematical coding from task 3, I can show the following figure. The blue stems are the low-resolution discrete samples. The red line is our 16 times higher resolution sine C interpolated continuous curve. Because the Nyquist bin splitting, energy scaling, and the T nu time axis were perfectly implanted, you can see that the continuous red curve flawlessly passes through the exact center of every single discrete blue point without any time shift. These are my problems, and thank you for listening.